Welcome to the second part of the lesson, which continues our overview of the Java object-oriented programming language. Most programming languages support a range of data and control abstractions, which make it easier to simplify the development of robust apps that are able to evolve flexibly over time. However, object-oriented languages go above and beyond data and control abstractions. In particular, Java supports more advanced object-oriented concepts, including inheritance, which enhances code reuse by allowing a class to receive methods and fields defined by another class, and polymorphism, which enables transparent customization of the methods inherited from an existing class. After completing this part of the lesson, you'll understand what these advanced object-oriented concepts mean, know the benefits they provide developers of Java apps in Android, and be able to identify Java features that implement these concepts. Although these advanced object-oriented concepts and Java features are powerful, they may take some time to understand fully. Subsequent lessons in this MOOC therefore examine Java inheritance and polymorphism in much greater detail, so you'll learn how to program these features effectively. Object-oriented programming languages enhance reuse by allowing classes to inherit commonly used state and behavior from other classes. Inheritance in Java is specified via its extends keyword. When a class, called a subclass, extends another class, called a superclass, the subclass automatically inherits all non-private fields and methods defined in the superclass. Private fields and methods are not visible to the subclass. For example, Class B is a subclass that inherits mField1 and method foo from the Class A superclass. Apps that use instances of Class B can therefore invoke both the method foo inherited from Class A and the method bar defined by Class B. This lesson uses the Java Collections framework as a case study to demonstrate the capabilities and benefits of inheritance, which enables the reuse of existing Java software components. This framework defines a hierarchically organized set of classes and interfaces that implement commonly reusable collection data structures, such as lists and maps, which are covered later in this MOOC. Here we'll examine a portion of the list hierarchy, which are collections that implement the list interface and maintain an ordering for their elements. The Java Abstract Collections superclass provides a skeletal implementation of the collection interface. This superclass forms the root of the hierarchy of collection subclasses that provide various implementations of ordered and unordered groups of abstract data type elements. Likewise, the Abstract List subclass extends Abstract Collection to provide a skeletal implementation of the list interface, thereby minimizing the effort required to implement this interface using a random access data store, such as an array. Various concrete subclasses, such as vector and ArrayList in the Java util package, extend Abstract List to provide implementations of the list interface using dynamically resizable arrays. This inheritance hierarchy enhances systematic reuse of both data fields and methods across list-related subclasses of the Java Collections framework. All Java classes directly or indirectly inherit from the object superclass that resides in the Java Lang package. This superclass defines methods that can be used by all non-primitive types, such as classes and arrays. For example, object defines methods that return an integer hash code for an object and use this hash code to check whether two objects are equal or not, as well as methods that objects can use to coordinate their actions in multi-threaded programs. Subclasses that don't explicitly extend a superclass implicitly inherit from a Java Lang object. For example, the Java Lang process class doesn't explicitly extend any superclass, so the Java compiler implicitly inherits this subclass from Java Lang object. All instances of Java Lang process therefore also provide clients with access to the inherited Java Lang object methods. As you may have noticed, Java Lang object is the most general of all classes, since it serves as the root of the hierarchy of classes available to Java apps. Classes toward the bottom of this inheritance hierarchy provide more specialized behavior by overriding methods that are defined above them in the hierarchy. For example, the vector, ArrayList, and linked list subclasses in the Java util package implement their particular semantics by overriding certain methods defined by list-related superclasses higher up in the Java Collections framework hierarchy. Subclass methods inherited from a superclass are generally used for three purposes. To make this discussion more concrete, We'll illustrate these purposes with an example of the generic stack subclass defined in the Java Collections framework. This subclass extends the generic vector superclass to define a last-in, first-out, or LIFO data structure that enables apps to push and pop items to and from the stack, respectively. The first purpose for extending a superclass is to augment the methods defined in the subclass API. For example, the stack subclass inherits fields and methods from the vector superclass. This code snippet shows how the isEmpty method inherited from vector can be invoked on an instance of stack to determine if the stack is empty or not. The second purpose of inheritance is to use methods defined in the superclass to implement subclass methods. For example, the stacks push method is implemented by the addElement method inherited from vector, which is yet another example of systematic reuse that's enabled by inheritance. The third, and arguably the most important purpose of inheritance, is to override superclass methods in the subclass that have the same signatures. In Java, method signatures are considered the same if the method names are the same and the number and types of method parameters are also the same. For example, the HashMap subclass in the Java Collections framework overrides methods with the same signatures as abstract map superclass methods, such as put and entry set, which associate values with keys in a map and return a view of the mappings contained in a map, respectively. Method overriding enables a subclass like HashMap to transparently customize the behavior of a superclass like AbstractMap, as we'll discuss next in our coverage of Java polymorphism. This upcoming discussion will also explore the ways in which AbstractMap methods can be overridden to define different mechanisms for associating values with keys in a map and returning a view of the mappings contained in a map. It's possible to apply inheritance in isolation to systematically reuse existing superclass methods and fields. In practice, however, inheritance is nearly always applied in conjunction with polymorphism, which is a key object-oriented concept that enables transparent customization of subclass methods inherited from a superclass. Polymorphism and inheritance are essential to achieving the benefits of the so-called open-close principle in object-oriented design and programming, which states that a class should be open for extension, but closed for modification. Insulating a class implementation from modifications helps make the class more robust and flexible, since it can be extended and reused without introducing new bugs to existing code. In particular, the open-close principle can be applied in conjunction with various patterns, such as factory method, which defines an interface for creating an object but leaves it to the implementation of that interface to decide which class to instantiate. In this case, the polymorphic methods of a class can be customized without modifying its existing source code or modifying the source code of apps that use instances of the class. Subclasses of a superclass designed in accordance with the open-close principle can define custom behaviors that are more suitable for a particular use case while still reusing the structure and even some functionality provided by their parent superclasses. For example, vector and ArrayList are subclasses in the Java Collections framework that inherit reusable methods from the abstract list superclass. However, the implementations of methods in the vector and ArrayList subclasses emphasize different properties of a list, such as synchronized versus non-synchronized element access, and different strategies for dynamically growing the underlying buffer when its size increases. Java apps apply polymorphism when a reference to a superclass is used to refer to an instance of a subclass. Methods in the subclass can selectively override methods with identical signatures defined in a superclass, thereby customizing their behavior to achieve the desired subclass semantics. For example, the abstract map class in the Java Collections framework contains methods that can be overridden by concrete subclasses, such as treeMap, HashMap, and concurrent HashMap. In particular, the put and entry set methods in abstract map can be overridden to define different mechanisms for associating values with keys in a map and returning a view of the mappings contained in a map, respectively. The subclasses of abstract map have different time and space trade-offs that are appropriate for different apps in different circumstances. For example, HashMap's implementation of put uses a hash function and an array of buckets to resolve collisions, which is suited for apps that want good performance in average and best cases. In contrast, treemap's implementation of put uses a balanced red-black tree data structure, which is suited for apps that want consistent performance even in the worst case. An app that invokes a put method call on a reference to an abstract map can be extended transparently via the open-close principle, so the appropriate put method implementation is dynamically dispatched at runtime based on the object type of the concrete subclass that extends the abstract map superclass, such as tree map, hash map, or concurrent hash map. By applying the factory method pattern together with the open-close principle, the app code needn't change, even if the makeTree factory method creates a different concrete subclass when it's called at runtime. Object-oriented programming concepts are at the heart of modern app development and mobile and cloud computing environments. Java has been one of the most popular object-oriented programming languages since its inception in the early 1990s, which is why Google selected it as the programming language of choice for developing Android apps. Now that you've completed both parts of this lesson, you should understand what key object-oriented concepts like abstraction, inheritance, and polymorphism mean in the context of Java, know the benefits they provide developers of Java apps in Android, and be able to identify Java features that implement each of these concepts. However, don't worry if you don't fully understand all these object-oriented concepts and Java language features yet, since the remaining lessons in this MOOC examine each feature in greater depth, analyze detailed code walkthroughs, and reinforce the lessons with assignments that enhance your knowledge of programming Java for Android. There are also other excellent resources available online, including the official Java tutorials and the Android API documentation. So please leverage these online resources frequently as you progress through the MOOCs in this specialization.